Welcome to Networks Professionals.
Okay, so let's just dive right into this. Picture this scenario. You've got two computers sitting right in front of you, right? You grab a standard network cable, you plug it directly into both machines, and absolutely nothing happens. Zilch. So why might plugging two computers directly together fail? I mean, it seems like it should just work seamlessly, doesn't it? Well, solving this little practical mystery is exactly why understanding the physical rules of our networks is so incredibly important. Welcome to today's Explainer. Today, we're taking the invisible, abstract rules that govern our digital world, and we're translating them into the physical, tangible cables you can actually hold in your hand. We're getting into the physical network, Ethernet standards, and cables explained. Honestly, if you've ever stared at a super messy server room or even just the back of your home router and wondered why we use specific wires for specific jobs, you're absolutely going to love this. So here is our game plan for today. First up, Ethernet speeds and standards. Second, wiring, straight through versus crossover. Third, pushing boundaries with fiber optic. And finally, decoding UTP cable categories. Let's get to it. All right, kicking things off with Section 1, Ethernet speeds and standards. And that brings us right to the ultimate rulebook, the IEEE 802.3 standard. Now, I know that just sounds like a random string of engineering numbers, but this foundational standard is what ensures all network devices, literally regardless of who manufactured them, speak the exact same physical language. It defines the speeds we can expect, and crucially, the exact type of cabling required to achieve those speeds. It is the absolute bedrock of modern networking. We can actually see a really clear evolution of that shared language when we compare fast Ethernet to Gigabit Ethernet. Fast Ethernet, which runs at 100 megabits per second, was the foundation of basic desktop connectivity for years. But contrast that with Gigabit Ethernet at 1 gigabit per second. This is the gold standard for modern local area networks and workstations today. We're talking about a massive 10-fold leap in everyday network capabilities that just completely transformed how quickly we can move data across a room or, across an entire office building. Let's break down the specific parameters for the legacy side of things first. Under the IEEE 802.3u standard, which is affectionately known in the industry as 100 bays TX, fast Ethernet gives us that 100 megabits per second. To pull this off physically, you need UTP, which stands for unshielded twisted pair copper cabling. Specifically, Cat5, Cat5e, or Cat6 will do the trick here. But listen, here is the absolute most vital detail to remember. There is a rigid physical limit. You can only push that electrical signal up to 100 meters over UTP before it degrades way too much to be useful. So the really crucial point here is what happens when we upgrade. Under the 1000 base T standard for Gigabit Ethernet, you're pushing drastically more data. And because of that, the baseline physical requirement shifts. Older Cat5 cabling, it simply won't cut it anymore. You absolutely need Cat5e or higher, like Cat6 UTP, to handle that kind of throughput. But hey, what if copper isn't enough for your needs? Well, this standard also introduces an alternative pathway, 1000 base SX, which completely ditches copper altogether in favor of fiber optic cable. Moving right along to Section 2, wiring, straight through versus crossover. Okay, here is the answer to our two-computer problem from the very beginning. When you're connecting different types of devices, like, say, a switch to a router, you use a straight-through cable. The pin-out standard, either T560A or T560B, is exactly the same on both ends of the cable. One device naturally transmits on the exact pins that the other is listening on. It's perfect harmony. But if you connect similar devices, like a computer to a computer, they both try to talk and listen on the exact same pins. Boom. It causes a data collision. A crossover cable physically swaps the transmit and receive wire pairs from one end to the other, literally crossing them over, so the data flows without crashing into itself. But you know what? Here's a fascinating real-world update for you. If you actually went and tried that computer-to-computer connection today, it actually might work. Wait, why? Because of modern auto MDIX technology. Devices today are incredibly smart. They basically have a built-in traffic cop. They can digitally detect if a collision is going to happen, and then automatically reassign the transmit and receive functions internally, right on the fly. It's a brilliant digital solution to what used to be a strictly physical problem. Pretty cool, right? Let's pivot to Section 3, pushing boundaries with fiber optic. So on one side of the ring, we have our familiar UTP copper. It uses electrical signals, which are great for standard office use, sure, but they're severely limited by distance and they're super susceptible to interference. On the other side, we have fiber optic. Instead of electricity, it uses rapid pulses of light. And guys, this is an absolute game changer. Because it relies on light, it's completely immune to electromagnetic interference, or EMI. Think about it. If you're running a network through a busy factory floor with heavy, noisy machinery that would totally scramble a standard electrical copper signal, fiber optic just ignores it entirely. Now, there are two distinct architectural advantages here. First is single mode, which essentially shoots a laser straight down a tiny glass core. We're talking often as thin as a single human hair, and it does this for incredible multi-kilometer distances. Then we have multi-mode, which uses slightly wider cores and LEDs for shorter but very high-capacity runs. Because it easily blows past that rigid 100-meter limit of UTP copper we talked about earlier, fiber is the undisputed champion for high-speed, long-distance communication. It acts as the backbone, carrying massive amounts of traffic between different switches and even entire buildings. And finally, Section 4, decoding UTP cable categories. There's actually this escalating potential hidden right inside these everyday cables. From the outside, they might all look like identical pieces of plastic wire, but the internal engineering is vastly different. We've got a baseline drawn by the ubiquitous Cat5e, which holds steady at a 1 gigabit per second capacity. Then we see a jump up to Cat6, and eventually we peak at Cat6a. Basically, the tighter the internal copper wires are twisted together, the less they interfere with each other, which translates directly to higher data capacity. Let's dig into the details on that. Cat5e is your standard modern workhorse, fully supporting up to 1 gigabit per second. But Cat6 is where things get really interesting. It gives you that same 1 gigabit standard, but it has a bit of a hidden superpower. It makes massive 10 gigabit per second speeds entirely possible over regular copper. However, there's a huge caveat you need to remember. It can only maintain that 10 gig speed over significantly shorter distances. For reliable 10 gig at longer distances, you absolutely have to step up to the further evolution, which is Cat6a. But across all these standard copper UTP runs, I want to burn this single number into your memory right now. 100 meters. That's roughly the length of an American football field from end zone to end zone. That is the defining physical limitation for standard Ethernet environments over copper before your signal drops and your network just starts dropping packets. When network engineers design buildings, when they run cables through ceilings and place network closets, this exact number dictates almost every single physical decision they make. So let's wrap this all up. We've gone from the invisible IEEE rulebooks all the way down to the physical twists of copper and the tiny strands of glass that make the internet possible. Next time you plug into a network, or honestly, even just look at that little cable plugged into the back of your Wi-Fi router, ask yourself, what category is carrying your data right now? Is it a straight through or a crossover? Knowing the physical rules really changes how you see the entire network. Thanks for joining me on this explainer, and keep questioning how your world is wired together.
Thanks for watching.